All right, start out with, are there any questions on, let's narrow it down to chapter 5 homework problem.
Yes,
Harrison.
on number, yeah, I guess it's, number 6, which is the second question.
The dog team, okay?
When calculating the tension, why do you add the friction to the acceleration?
All right, so problem number 6. All right, so I've got dogs, sled, a connection, and say they're going that way. So thinking about the forces, they're pushing against the ground pushes against them, so I don't think that they specify what kind of force that is. 185 newtons pushed backwards on the snow for times 8. So there's a force in this direction of, what's it, 185 times 8.
Yeah.
There's some friction acting back, so this is, let's call it force from dogs, since they don't specify. Then there's a friction acting back on, I'm guessing just on the sled.
Yeah, the picture only had it on the sled, I didn't know.
Oh, picture in the solution.
In the solution,
Okay.
yes.
So if we look at it as a whole unit right here, this tension is an internal force. So we ignored the internal forces.
Right.
So it's basically that minus that should equal mass, total mass times acceleration.
Okay.
If we then break it up into, let's look at just the dogs and let's look at the sled. And there's a rope in between or some connection between them. There's a tension pulling here, there's a tension pulling here, tension pulling here, and then we have the force from the dogs and friction.
And
So-
is there another tension on the rope on the other side? Like
Oh,
right
yes,
there?
yes, thank you. So from the first part, I already know what the acceleration is.
Right.
And I'm assuming the dogs and the sled have the same acceleration.
Yeah.
So therefore, I can do F dogs the force from the dogs minus the tension is equal to mass of dogs times acceleration. Or I could do tension minus the friction is equal to mass of sled times acceleration. Whichever one that you're gonna do, you should get the same answer, similar to the tug of war problem in the previous chapter. But if you add tension to both sides, or I guess they added friction to both sides.
Yeah.
So that they were looking at this equation and then solve for tension.
Okay.
Does that answer your question on that?
That does, yeah.
Okay.
And then why is there like from the dog's like paws to the ground, like there's no, we're just worried about the friction on the sled, like is there no friction from the?
All right, so the dogs are pushing against the ground. Now, how are they pushing against it? Are their feet barreling, basically going into it and then pushing with a normal force, or is that friction? The way I read the problem here, and if I solve the solution, I might interpret it differently, but the way I'm reading the problem is that the friction between the dogs and the ground is already bundled up in this.
Okay.
Because their paws are pushing backwards, so any friction is in that direction.
Okay, gotcha, that makes sense.
And in reality, this is probably some combination of friction and normal force, because their feet do sink in,
Okay.
I assume, unless they're elves.
Okay. Yeah.
How do you get the question C in the same question?
So,
How do you find it?
the magnitude of the force in the coupling, so if you look at, that's what this is, that's what the tension is. So we have two forces basically acting horizontally on the dogs, two forces acting horizontally on the sled. And so if we look at the sled, the tension minus the friction is equal to the mass of the sled times acceleration. So what you're doing is just solving for that. Is that sufficient, or?
I tried to do that, but I got something else other than 980.
What was the acceleration?
For the first one,
Yes.
3.29.
I said meters per second squared.
Uh-huh.
And mass of sled,
210 with the
with
person.
rider. And I am assuming the rider's not falling off. So this becomes the tension, or the force from the coupling, whatever the connection mechanism is, minus the friction, which would be UK times Y, is equal to mass of the sled times acceleration. Was, yeah, 210. In this case right here, looking at those forces, we have a normal force acting up and we have a weight acting down. I am assuming that the connection here is horizontal, or parallel to the ground at least, and horizontal. And so therefore, in this particular case, the normal force would be equal to the weight, just because there's no other forces there. And the formal presentation would be y minus w is equal to 0, and therefore y equals w, which equals mg. So my tension, therefore, is 210 times the acceleration plus mu k, whatever that value is, which, if my memory serves me correctly, is on page 175. And that was waxed wood on wet snow, that's 0.1, times 210 times 9.8.
So that has to be 980.
The total?
Uh-huh.
All right, so that's gonna be 6 something. And that's gonna be 2 something. At a quick glance, 980 doesn't quite seem right, but, because this would be about, this is roughly 660. And this would be roughly 200. I'm getting somewhere around 900. You said 980?
It says 980 in the answer here.
Oh,
That's why I was confused. I didn't get 980.
did they use 0.14?
Yeah, they use 0.14 for static.
Yeah, I don't think static is appropriate here. Oh,
But it's case
starting
by-
from rest.
Yeah.
Yeah, I just usually don't look at it that way. What the textbook does is you need to overcome that static friction first. And so therefore, that is so the resistant force is that maximum static, only at the very beginning. And so once you get moving, that quickly drops off. So that's their approach. On test, I definitely, it's either moving or not. I'm not worried about that immediate force.
Just going back to this again, so they had it where it's the mass times, and then in parentheses, the acceleration plus u sub s times g parentheses. So why is it not just the mass times the acceleration just plus the value of u sub k times g, or u sub s times g?
Is this a question about, okay,
This
so
is
it's
just
not,
like
not a
the-
US UK issue, but.
No, just like the order of operation, like I guess how to, because I thought so you're just adding the friction
Yeah,
like to that side, so I thought that it would just be like the mass times the acceleration just plus the value of the friction.
it is, and
Okay.
what they've done here is, so we have tension minus mu s, instead of k, mg is equal to ma. So the tension therefore is ma plus mu s mg, which is m times a plus mu s g, which I assume is what they did.
Okay, yeah, okay.
It's just a matter of how you wanna crank it out.
Okay.
Typically in physics, you don't plug any numbers in until the very end, and you try to simplify it as much as possible. Now, is that much simpler than that is? The authors apparently thought so,
Gotcha.
but just adding the friction to mass times acceleration.
Yeah, I
Perfect
forgot,
analogy.
I forgot the M in the MG with the, I was just doing U sub S times G and forgot the other mass, and so I was confused why they did
Ah.
all of that, yeah, okay, that makes sense.
Good now?
Yes, thank you.
Right. Other questions from chapter 5 homework problems? And, oh, Anna?
One general question, when we're trying to show that you're overcoming static friction, which maybe that doesn't apply to the quiz, but like, do you have to work through all of the steps, or can you just do the mu sub s times whatever the normal force is for the problem and show that that is greater than or less than?
There's a large group of problems where you can get away with that. Where you can just show, hey, here's the maximum static, here's the force in the other direction. It doesn't
Right.
overcome it,
And then just
done.
do all the calculations with u sub k and not double back.
Right, right. I'm not saying that there are not problems where it's more complicated than that. And you really should go through all the steps. But if you can get away with a shortcut, great. If you try to get away with a shortcut when it's not appropriate, I'll understand, but part of me will die inside. Not that's putting any pressure on you. Harrison, you look like you were about to ask another question.
No, I'm good, thank you, yeah.
Anyone else have a question? Brooke?
How do we tell if an object is moving again based on the friction? Like, how do we know if it's like overcome the static friction? It's like
The way you generally do it is you calculate what the maximum static friction is. So
okay.
that's mu s times the normal force.
Right.
And so if the force in the opposite direction is greater than that, it's gonna move.
Okay.
Sometimes life is just nice and the problem says, an object's already moving. Or speed is not zero. It depends on my mood when I write the test. Just remember on the test, the harder the problems are, the more faith I have that you can do it. That's because I believe in you.
I don't know if that's what's gonna be going through my head on the test.
That's right. I know I can. The little engine that could, that's physics right there. You just believe you can. And if I mark it wrong, it's because I'm beneath you.